Hello. Okay, so yeah, let's begin. I hope my screen is visible to you all, and we have reached to the last week, which is 12 week 12 of our doubt and problem solving session of carbon materials and manufacturing. So I hope that whatever we have discussed till now, all the concepts and the problems are clear to you, and hopefully this course you have enjoyed and you learned a lot from these tutorials and problem solving sessions. Now since it is the last week, so I am open to you all to get any questions from you guys. Whatever questions you have, you can ask me, and also if not now, you can email me. And if not, then we can start our last session. Okay. So since till now, whatever we have discussed is mainly related to graphene, carbon nanotube, graphite. How can we, characterize this by various kind of characterization techniques such as Raman spectroscopy, X-ray diffraction, transmission electron microscopy, scanning electron microscopy. So these are various kinds of techniques through which you can characterize your material. Um, and also there are, apart from this surface characterizations, there are many um characterizations which such as your electrical characterizations, which will give you the electronic property of your material, as well as to find out the mechanical behavior of your materials, such as the Young's modulus, as well as uh, the yield strength and the ultimate tensile strength of your material. You can go for the mechanical characterization of your material. So in a broad perspective, all of this, from beginning to having a knowledge of any material, and then synthesizing of that material. After that, on a lab scale, you have to do certain kind of a characterization, such as your surface characterization, electrical characterization, mechanical characterization. So these are a few types. After that, from a lab prototype or a scale level, you have to take this to the industry level, that how can you manufacture this. So this is a very long process, but in a nutshell, it is quite interesting. And the interesting field, when you want to do some field work or some work or some research work by taking carbon as your material. So yeah, so let me take my pencil. So today we'll see some problem statements, and we'll try to solve these problems, as well as some more concepts, that how can we take this to the industry level, and many more. So till now, what we have discussed is like firstly, the first I will write it down from the step by step. So the steps are: the first thing, you should have the knowledge. Okay. Second thing is that your synthesis of your material. Okay. Synthesis of your material. Third thing is your characterizations. Characterization, let's say your surface characterization, your electrical characterizations, and you can also do some mechanical characterizations. The fourth point after this, okay, you got this all the knowledge about this, then you have to think that how can you, scale up, that how you can industrial, how can you level, how can you take this material for the main purpose of this, I mean, where you can properly use your material for the manufacturing of some big parts, such as that can be used in aerospace or aircraft or somewhere else. Okay, then only it will have some benefit out of it. Without this, on a just otherwise, if we will restrict this to the research lab level, then it won't be a good beneficial. So the main thing is large scale manufacturing of carbon structure. Okay, so graphite, glass like carbon. So you have to manufacture in a large scale. Okay, up to the research, research lab scale, it is quite fine. Okay, you can manufacture it, but it is very very important for nowadays that whatever you are doing, that should be in a scale, that should be scale up. You can easily scale up that manufacturing process. Okay, so here, let's say you are taking some graphite, or you can take a glass like carbon, and you can take any composite based on the carbon, such as carbon polymer and the carbon, and you can take any one. Okay, so you have to make it to the large scale or the industry scale, okay, level. Okay, so in this case, what will happen, the graphite flakes and a small crystallite can also used as a powder. Okay, so this can be used as a powder. It can be having any shapes. Suppose you have a flakes, you have a spherical particles. Okay, so it can be used as a powder. This saves is given to the precursor material prior to carbon material development. Okay, so firstly, before any development of this material, this shape, okay, is given to the precursor material. Okay, so whatever shape you want, let's say you want some um, so let's say you want a flag, you want a needle, you want rod like structure, you want spherical, so there could be a many more. Okay, so that depends on the precursor. So if we are using a solid precursor which cannot be formed, example, a needle coke, graphite flake. Okay, so in this all, whatever you are using, a binder is essential. Binder, the main purpose of your binder is to, make your it will contribute your process. It can also have to gain the size whatever you want, and it will ease your manufacturing process. So after forming, the structure is carbonized at the desired temperature. Okay, so forming, if you know the forming, like we have discussed in 2 3 lectures before about this forming. Okay, so if not, then you can watch that lecture. So structure is carbonized at the desired temperature. So carbonizations also, I have taught you guys that what is the carbonized. And for every material, let's say, you will have a CNT, or suppose you will have a graphite. So every material has their own, certain specific temperatures where your carbonization process will take place. Okay, it should be optimized. It should not be a very high temperature such that your material will burn out, and it should not be something like a very low temperature where your materials could not carbonize properly. So the pore filling and structural shrinkage are two main challenges. Okay, pore filling, it means to say, let's say if your material will have some pore, or your material is kind of a porous, and it, st- structural shrinkage. Okay, after this process, sometimes you will find your materials got, suppose this is your material, it has a thickness of, let's say, 5 centimeter, but due to certain reason it will shrink. Suppose from half it will shrink, so it will become uh, half of suppose if it will shrink up 5 then its thickness will reduce. Okay, from 5 centimeter, so it will be around 4 to 4.5 centimeter. Okay, so these are the main challenges. So the structures from carbon composites are also manufactured in similar fashion, but their patterning is also done using composite manufacturing process. So here your structures, there are, I mean, I have taught you that carbon composites are also manufactured in similar fashion, but here the main thing is your patterning. Okay, so patterning is done using a manufacturing process. So like there are a lot of manufacturings like additive manufacturings and whatever. So here mostly they are using a molding. Okay, so molding is also related to, you will have a mold. Okay, you will, molding means you will have a mold, and after that mold you will put your material to get a desired shape or the structure whatever you want. Okay, now 3D printing is something which is quite interesting field. So 3D printing itself, by name itself, you will get a sense that here something is built up by use in three dimensional. Okay, so suppose if you are using your material in any form and you want to create some kind of a certain structure, you can modify it and you can make a variety of structures by using your 3D printing. So here the main purpose of this material, this manufacturing process is that it has wide range. You can make any shape, you can make any structure, you can make a wide range of size from level to meter level, and you will have a easy process. Okay, I mean it should not be a very difficult. So nowadays it is quite interesting and many people are opting for the 3D printing because of its easiness. Now the precursor here, let's say you can have, like I have just, like I have told you, like this precursors materials is very important for the development of any material, let's say a carbon material. So these precursors can have in the two forms. The first form could be your solid, and the second thing could be your semi-solid, or it could be in the form of a viscous liquid. If it is a solid, then you have to mix with a binder in order to change its surface tension or the surface property here. Okay, so here you have to add plus binder. This binder could be anything. You can use some polymer or any resins. Okay, so this is something like that, just to make your whatever you want, some shape or structure. So for the solid, if your material is solid, then you have to have this binder or this polymer as a binder material. Then only you can further go for this forming technique. Okay, this technique where you will give the main shape to your material. And if you will have some, a gel kind of or the viscous, then you don't need of mixing it with a binder, because the main purpose of binder is itself you have to make or modify the surface property. But here you do not require your binder. No binder. Okay, so in this case, you will directly go for the forming. And after making a certain shape, you want to become it hard, or you want that shape, so you have to expose it to some temperature. Okay. So when only after the heat treatment, you will get that final material. Okay. Let's say here you can see these are some material, and you mix this with this material, and it lasts after this all the treatment, you will find this kind of a shape. And if you will look at this, these are like a small particles of that whatever the material you want. So the main analogy of this material, or this manufacturing process, is that you should have, first thing is your precursor. Precursor, that's mean that whatever things you are using, suppose a solid or a liquid for development of your material. Okay, so you can go for the in solid binder, and then you will go for the forming process, and then in order to get the final, you require a heat treatment process. Now, if you will have activated carbon and carbon black, then what you will do? Suppose activated, or that is your porous carbon also. So here is your porous carbon and the carbon black, and some low purity cars are often used in bulk as pellets, cylinders, or powder. Okay, so here also you will be using these things as a powder. So large scale structure such as water purification columns are prepared by packing columns with the pellets powder. Okay. Packing column, pellets or powder you will require large for the large structure manufacturing. Carbon black is generally mixed directly into the rubber material. So here also what you will do, you will have a carbon powder. Now it is in the solid form. You will mix this with your rubber or let's say a polymer matrix. So what will happen in this process? This will also nothing but as a binder. Okay. So when you will mix this, it will change the property. Now the activated carbon black fibers are used as a membranes or the bundles. Now, in some cases, what will happen? The fibers may also be braided or woven. So, catalytic carbon beds or some structure with predefined shape can be made using formable mixtures of porous carbon precursors followed by carbonization and activation. Okay. So, here what it is saying is that suppose you want any some shape or some structure, then there will be a suppose if you want a carbon bed. Carbon bed or any kind of a structure, then after that what will happen, you have to make made using formable mixture of porous carbon. Okay, so you will make a mixture of your porous carbon. Okay, after that this process what you will do, you will followed by you will do the carbonizations or let's say activations. This you already know that what is carbonizations, what is activations, which we have dealt in our earlier lectures. So after this process, this activated carbon in pharmaceutical is used as pellet or pellets plus binder. Okay, so even in pharmaceuticals what will happen, this activated carbon, this can be also in the form of powder and you have to make some mix with this binder, then only you will get some structure. Other applications include some cosmetics, filtrations, organic molecule observers, where powders are most commonly used. Okay, so here what will happen? So here let's say you can use this as a filtration. Okay, so what will happen in so this filtration you can use in the water purification, water purification technique. Okay, so what will happen? So here this is like a membrane shape from where your water will go, and whatever the heavy ions or the arsenic materials which you don't want, that will filter out and you will get here a pure water. Okay, so in one way you can use this activated, that's why in many kind of commercial ads you have seen this, they are using this technology and they are filtering the water. Okay, so I mean there are this is a kind of a membrane filter, here you can clearly see. So here you will have this kind of a membrane. and in this you will have, and there you will have a series of this membrane from where your water will go in and out. So this will give you a many steps, multi-steps filtration process, which requires in order to remove the contamination from your water, that will give you the pure water so that you can, it can be a drinkable grade water. Okay, so this is a very good applications and many research are still going on. So yeah, this is a one kind of a very interesting and emerging technologies where we can use this activated carbon and our carbon black for these applications. Do you have any doubt? If you have, then please ask. We can discuss it now. Okay, if not, then we'll go ahead. Now, the carbon based micro and nano devices, top down approaches. So, you all know that. So, there are two processes, two types, top down, which will go from top to down, and there is a opposite, down to top. Okay, in manufacturing process. So, here the graphite, glass like carbon, porous carbons, carbon fibers, and various carbon nanomaterials such as your graphene, carbon nanotubes, vapor, vapor-grown carbon fibers, and fullerene are used in micro nano devices. So these are mainly which we have learned in this courses like graphite, glass-like carbon, graphene, graphite, carbon nanotubes, porous carbons, activated carbons, carbon blacks. So these are prominently used in the field of micro nano devices. Okay. So the main advantage of using this kind of a material is its properties. Various properties such as your electronic property, mechanical property. They give the property so that this is that fulfill the requirement of your micro and nano devices. So that's why these materials are using in various fields such as your as a membrane in your water purifications, as a sensors, or as a energy storage applications, and many more. So this device fabrication using glass like carbon, carbon fiber, and some porous carbon can be using a top to down techniques. Okay, where your manufacturing will start and it will opt the top to down techniques. Phenol formaldehyde resins, furon resin, some hydrogels, and some acrylic polymers can be converted into glass like or similar carbons. So it means that there are many kinds of if you want a glass like carbons or some similar feature, then there are many hydrogels which are currently in the developing states, and also there are some acrylic kind of a polymer. So this can be used, convert into glass like or similar carbons. So these polymers can be lithographically patterned and heat treated. So like I have told you that what is lithography. So lithography is a technique where you will transfer your pattern. So it is a process where your whatever desired patterns you want, that can be transferred. Okay. So by using your lithography, and after lithography process, it is followed by your heat treatment. Heat treatment technology. So heat treatment is required for this process. After that, structures are surface bound, hence very high temperatures are not possible. Okay, due to use of substrate, Here, because it is a surface bond, so we cannot expose this to the very high temperature. Dimensional shrinkage is not isometric also here, and very high surface to volume ratio can be obtained. Okay, so that's mean the surface to volume ratio means the surface will be high, and surface to volume ratio, okay, it will be a very high, and micro scale structures can be converted into the nano scale, so that it will be a good useful for the nano devices. So that's why here you can use this for the micro devices as well as for the nano level device. So the combination of different techniques and carbon materials can be used. Okay, so here you can use a different techniques and different kind of a carbon material. And example is a carbon fiber can be combined with lithographically patterned carbon structure. Okay, so here you will get also lithographic pattern carbon structure, and you will have a carbon fiber. So like as I have discussed, so here you will have a carbon fiber. So you are sorry, carbon fiber. So this you can get easily get by, you can use a electro spinning kind of a technique, where you can make a carbon fiber, and this carbon fiber will mix with your lithographically patterned carbon structure, and then you can use this. Also you can use a combination of ceramic metal, silicon, and other materials are also common. Okay, so here you can see in this image, this is a this is a tip kind of a shape or a structure, glass like carbon electrodes plus CNF. So this is electrode. Here you can see this. Here this is glass like carbon electrode. So here it is very beautifully patterned and very it is in a micro nano level, and this is your cell culture on carbon. Okay, so here you can see, you can also use this for growing a cells in your carbon materials. That is also a very good applications in this field. So yeah, overall, if you will see in this top-down process, so you can use this for a variety of applications. Like you can use many kind of a carbon, such as your carbon fiber and your, let's say, a carbon black, or you can take a glass like carbon and some carbon fiber, carbon nanofiber you can use, or glass like carbon. So that can be used for making an electrode, or for making some surface where you can grow your cells. So yeah, this is a very good applications where you can expose your materials, and not just your single materials, but you can use that material by combining with the other materials, and it can be utilized for other many more applications. So if you have any doubts in the slides, then you can ask and we can discuss further. Or if you have anything, some good applications in your mind, that you can also uh, uh, discuss here. So let us discuss some good problems that will help to clear some concept. So this is a problem set where we have to calculate the required quantity of isotopically pure barium carbonate for achieving 1 millicurie activity. Calculate the equilibrium reactant constant for graphite to diamond conversion at STP, standard temperature pressure. If the energies of formation of diamond and graphite are 2.920 kilojoule per mole respectively, mention the feasibility of the reaction at STP and calculate the boundary layer thickness inside a CVD chamber of 1 meter diameter where a hydrocarbon gas of density 0.685 kilogram per meter cube and viscosity 0.55 poise is undergoing thermal decomposition onto a substrate of length 2 centimeter with a gas flow rate of 10 meter per second. Calculate the UV exposure time for a 20 micrometer thick resist film on a silicon wafer if the energy required for cross linking is 200 millijoule per centimeter square, and given the lamp intensity is also given 8.2 milliwatt per centimeter square. So let's discuss this problem and we'll try to solve this. So here the first thing is related to your radiocarbon. So here, if you remember when we were discussing our decay law, so this is nothing but the n equals to n naught is to power minus lambda t. Okay, so here n is what your it is unchanged. Okay, so which will be your unchanged. Now t half will be your 5745 years. So how much it will be? 0.693 by lambda. So this is your given. I have given you the hint and now I want you guys to solve and then take some times and try to solve this. Then it is the hint that how you can solve and then we will discuss this problem. So please try a few minutes and then I will discuss this problem with you. Okay, so I hope you got this problem, and if not, then let me just solve for you. So after this, what you will get? You will get lambda equals to 0.693 divided by 5745 into 365 into, because it is in year, so you have to make it till the second. Okay, so it will come around 3.83 into 10 to the power minus 12 per second. So atom decaying is proportional to atom present. Okay, so here after that, equals to lambda n and equals to lambda w by 199 into 6.023 into 10 to the power 23. So how much it will come? 1.16 into 10 to the power 10 watt per second. Okay, so this is your dn by dt. So after this, what will happen? 1, since 1 MCI equals to 3.70 into 10 is to power 7. So how much it will come? dn by dt. So here your W will be your 3.70 into 10 is to power 7 divided by 1.16 and 10 is to power 10. So it will be coming around, when you will divide and multiply and divide, minus 3 of gram. Okay, so this is the calculate this required quantity. So it will be W equals to 3.19 into 10 is to power minus 3 gram. Okay, clear? I hope this is clear. If not, then just let me know. Now it is saying the graphite to diamond conversion at STP if the energies of formation of diamond is 2.9 and 0. So mention the feasibility of the reaction. So whether it is a feasible or not, that we have to select. Okay, we have to tell the whether this is feasible or not. So let me take a new slide, and then we can discuss that. And let me take my pen also. Now here, since graphite to diamond. So here, when you will remember, when I taught delta D of reaction equals to delta, since it is transforming to diamond, so delta G of diamond minus delta G of graphite. It is given how much? 2.9 kilojoule per mole. And the value of this K is your e to the power, this is the formula, minus delta by minus delta G by RT. So here when you will put the value of this, then here you will have a minus 2.9. Since it is kilojoule, so make it convert into joule, and then the value of 3.14 into 273 since it is in STP. So how much it will come? It will be coming 2.278. So since your delta G is greater than 0 and K is your less than 1. Okay. So what it will be? It will be not feasible. Your reaction is not feasible. Got it? So this will be your answer. I hope you have gotten this. Yeah. So now the calculate the boundary layer thickness where your chamber diameter is 1 meter and your density of your hydrocarbon gas is your 0.685, viscosity is given, and thermal decomposition onto substrate length is 2 centimeter with a gas flow rate is 10 meter per second. Okay, so here, like, let me take another slide. Okay, so here the formula which we have discussed earlier, the boundary layer S equals to 1 upon this is what the Reynolds number, where how you will calculate this Reynolds number. The formula is your rho Vd by mu. So here as you can see, rho is how much given? It is given 0.658 kilogram per centimeter cube. Now V is how much given? It is given velocity is 10 meter per second. D is how much given? 1 meter. It is the mu is viscosity. It is given your 0.55. And when you will convert, it is 0.55 this. Now when you will calculate this, so in formula of Re equals to 0.658 multiplied by your 10 multiplied by your 1 divided by your 0.55. So it will be coming 119.63. It is the value of Re. This is 9. So again you have to put this value to this equation. So here S equals to 1 upon, sorry, this will be your, since it is given how much? 2 in the questions. So 1 upon 119.63. So how much it will come? The boundary layer thickness will be, when you will calculate this, sorry, 0.1828 centimeter. So this is your answer. I hope you've gotten this, but this is how you have to solve. If you have any doubt, you can ask now, or otherwise we'll go ahead. I'll wait for some few minutes, and if you will have any doubt, then you can ask. Let me discuss the last one. Last one is asking calculate the UV exposure time for 20 micrometer thick resist film on a silicon wafer if the energy required for linking is 200 millijoule per centimeter square given the lamp intensity. Okay, so let's discuss this also. So here the energy, how much they have given the question, 200 millijoule per centimeter square, and it is also given the lamp intensity, how much, 8.2 milliwatt per centimeter square. So resist data sheet you will get this, and how much it will come, then you have to divide this 200 by 80 and it will come around 24.39 second. So you can almost say this a 25 second. Okay, and for uh, SiO2 uh, glass, so it will you have to multiply it by 1.5x. This is, so from their data sheet you can get this further, and you can solve this in this way. So I have given overall this concept, and let's move to the again next question. The problem set is saying that mention all types of materials, method and parameters to manufacture the following: hollow hollow polycrystalline graphite, it is saying, cylinder that contains cast iron filling as shown in the figure. The top plate has a layered graphite structure with a mosaic spread of 0.8 degree between the top graphite plate and the cylindrical structure. There is a thin metal layer. The carbon in the bottom layer should be of lower purity and contain porosity. Note that after filling, iron should not be heated more than 900 degrees centigrade. There should be no glue adhesive or weak joints. So please try to solve these questions also, and let's discuss. I'll give you some few minutes and then try to solve by yourself. So let's try to solve this question also. I hope that you have gotten some idea, and let me give you, if I will not solve it completely, I will give you the hint that how it can be solved. So this is something like my diagram is not good. Sorry for that. So here you will have this follow kind of structure, and okay, here you will have some less purity, and here on top of this you will have this iron, and this is your this. So manufacturing graphite cylinder, so how you will manufacture this? So needle coke plus, so what you have to do, first thing is you will get a needle coke, and like as I have discussed just few slide backs, you have to mix it with some pitch, or you can add some resin as a binder, and then you have to expose this to the more than 2600, and you have to go for the heat treatment process. Okay, and second one is your you can do the casting of your iron, and then the third one is your pyrolysis, pyrolysis of your hydrocarbon top layer, and at the bottom for your, and at the bottom you will have a copper or nickel layer, and B is your, this is your A, this is your B. B you can opt for the hot pressing, and here also you will require a 2600 degree centigrade. Any polymer you can do some carrying process. So, and here the temperature is required 900 degrees centigrade, and you can mix it with any polymer. So there are a lot of all the steps, materials, methods, and parameters to manufacture the following. So this is that the manufacturer material and method. The first thing is your, what is uh, material, needle coke plus bleach or resin, and then you can go for your methods. In methods casting, you can go casting, and it is required also saying that the parameters and manufacturing, so the casting and pyrolysis, and then the hot pressing, and then curing, and these are the parameters that is required to in order to manufacturing whatever given in the problem statement. I hope it is clear. Now, the carbon-based, whatever the micro and the nano devices we have. So earlier we have seen the top-down, and now we have a bottom-up process. Okay, so in the top to down, we go from the top to bottom, and in from bottom up, we have to go from the down to top. So the carbon nanomaterials are most commonly patterned using bottom up approach, such as printing. Okay, so printing is very well known techniques, okay, that is majorly used for the printing of any kind of a carbon material, or you can use a carbon nanomaterials. So the properties of nanomaterial are often compromised here in bulk, when you will use this in the bulk. So the property, sometimes you will not get whatever you want. So this is, you can see the how beautifully printed here. So I think this is printing technology also. So this is a printing. So you can get this pattern. This is, I think, your carbon, and this is your track. This is your kind of a pad. and this could be your carbon. So the individual nanostructures here uh, have been used in many devices, but most of them have not been commercialized. Okay, so they have used for the many devices, but we are not using in a very bulk manner. So other than printing, you can opt for the spraying. You can go for the coating when you will have a carbon nanomaterial. So basically, what we will have in our printing process, in printing, you have to mix your material with some solvent, as well as you will have to use some binder in order to make it like a paste or some gel kind of a structure so that you can print. And in spraying, your nanomaterial, carbon nanomaterial will be there, and just mix it with some solvent, and then you can just spray coat it with some any substrate. And also in coating is also the same. You have to just coat in the surface of substrate that whatever the material you will require. And then the nanomaterial can also be mixed in other carbon materials, and it can be carbonized. So the applications of nanomaterial include a wide range of sensors, transistors, electrodes. So here what will happen such as sensors. So there are many kind of a sensors, such as your temperature sensors. You can make a pressure sensor or the humidity sensor. So basically the main phenomena of this nanomaterials, if you will be using, these are like a piezo-resistive. Okay, suppose if you will be uh, using in the application of your sensors. Okay, so this is mainly a piezo-resistive kind of a material. Okay, so suppose let's say if you are using a carbon, then you can use this as a, let's say, a pressure sensor. Okay, you can use this as a pressure sensor. So when you will apply the pressure, the resistance of your material will change. It could be like upside down, like increasing the pressure increase the resistance, or sometimes it can decrease depending on your material. But the main thing is that here your resistance will change when you will apply the pressures. Also when you will apply the temperature, or when you will apply the, or when you will vary the humidity, your this thing resistance or the capacitance of your sensor will vary when you will be using this kind of a nanomaterial. Also when you will be go for the transistors, you can use this to manufacture your transistor materials and some electrode material, which will be useful for your energy storage applications and also for some sensing applications. So the nanomaterials can be used as additives in composites also. So composite is a very vast field where we are using many kind of a matrix. Okay, so the use of nanomaterials is because of its specific properties, such as its high weight to high ratio, and also the surface area is high, as well as many unique properties such as your conductivity. If you want a good mechanical strength, you can use some nanomaterial or the nanopowder. If you want some electrical property, then also you can use some conductive nanomaterial. So in this way you can make your composite in such a way that it will be a good for using as a reinforcement in your matrix, and that will give the some specific property to your material. Also the nano and the micro 3D printing and multi-layer lithography can be used for making 3D structures. Okay, so here if you want some good 3D structures, then also you can, suppose if you want this kind, any such kind of a shape, suppose a needle kind of a shape, then you can go and you can just manufacture, and you can get some good shape by using a 3D printer. Here you can see this shape. This is how beautifully made, I think, by lithography some process. And here also these are the some aligned SW single wall carbon nanotubes, and these are the contacts, and these are connected, contacts are connected by this, and here you will get the contact, and you can use this kind of a material for your any applications. So I will have one question is to obtain a gas adsorption isotherm, what are the values plotted with respect to each other? Free and when you will gas adsorption isotherms, I have taught you. So what will be the values plotted with respect to each other? Free energy and the quantity of gas adsorbed, temperature, quantity of gas adsorbed, partial pressure, and the quantity of gas adsorbed, free energy, and the pressure of the gas adsorbed. So please guess and give me the answer and the reasoning behind this question. So its answer is partial pressure. So whenever we will do the gas absorption isotherms, so the value we will be plotting is the partial pressure versus the quantity of the gas absorbed. So the challenge, what are the challenges? Okay, so every device is not very common and very easy to make. So there are some challenges is also exist. So here the small scale devices have multiple components and the compatibility between these components is very important. Okay, so the compatibility means, it means to say, suppose if you will be making any device, then it is not always possible to use a single material to fabricate your device. So it is always advisable, not advisable, you will require a certain kind of a different material in order to fabricate your device. So sometimes it is very uh, difficult to make compatibility between your different materials. Okay, suppose let's say this is your material one and this is material two. So it should be compatible such that, oh, okay, I mean you can make easily selection of the right fabrication techniques. Okay, let's say you will have a material one which can sustain a higher temperature, but your other material, let's say material, it cannot sustain the high temperature. Okay, so you cannot opt the techniques which will go for the high temperatures because your other materials cannot sustain. Okay, so you have to select certain kind of a fabrication techniques that should be compatible with all the materials whatever is requiring in your fabrication process. Selection of precursors is very important in order to get whatever the shape, size, structure, and the properties you want in your device or in your material. Optimization of dimensional shrinkage. Okay, so it often it has often seen that whenever you will go for any fabrication techniques or the processes, there will be some dimensional shrinkage will often be found, and you have to optimize. Okay, suppose if it will be then you have to give the tolerance so that in order to avoid that tolerance and you can smoothly get your structure. And in case of printing, optimization of additive binder interface property. Okay, so it is very important that whenever you will do go for the printing process, suppose let's say there is 3D printing or some screen printing, then there are many kind of steps or the optimization is required because in any printing, okay, so whatever what is there. So let's say this is your printing, you will have your powder, or let's say you will have your nanomaterials. You have to mix your material with the binder in such a way that it should maintain its properties such as surface tension, let's say surface tension, viscosity, viscosity of your material, surface tension of your material, and fluidity of your material. So these are some properties whenever you will mix the binder. It is very important to optimize. Otherwise, if it will be a very viscous, it cannot print very smoothly, and if it is very dilute, then it will be messed up all around. So carbon metal interconnect. Okay, so work function difference and contact resistance will be there. So let's say you will have here, as you can see, so here you can see this is your metal, and this is your carbon. So here in this portion you will have some contact resistance. Okay, so this carbon metal interconnects work function because of the difference in the work functions and contact resistance. You have to also reduce this kind of challenges. Limitation of heat treatment temperature, as I have already said that because if let's say your material A can sustain a high temperature, but your material B cannot sustain that much higher temperature, then it is very difficult to fabricate the material. So you have to have some material or some techniques which can be suitable for both kind of material. Characterization, extremely small quantity of material is required for the characterization, and you can go with that. So these are some, and here you can see the carbon pillar of a very micro size. This is 1.6 and this is 2 micrometer of length and 1 micrometer of dia. So this is how you can make or you can overcome the challenges of making your this thing. इतना इतना 9 प्रकार 9 9 5 क्यों कल मान लें अच्छा ठीक है So yeah, so here flexible carbon structure and device, when you will see that so the all forms of carbon are generally hard and brittle. If you will see in a large scale, so but nanoscale materials such as you will have a nanotube and graphene are flexibles and as individual structure, but for technological application they are often used in bulk. So one can fabricate a flexible carbon structure using the following techniques, such as your printing carbon nanomaterial on flexible substrate. Flexible substrate, here you can see they are like polyimide substrate. So here you can see this is a polyimide. This is your nothing but your polyimide substrate, so which is a flexible substrate. It can be moved and it is quite flexible. And carbonizing a flexible substrate by using your laser carbonization or polyimide film. So here this is flexible carbon structure made by laser. So here what will happen, this is your suppose this is your sheet and here the laser will come and that will carbonize your polyimide. So this is your carbonizations of your polyimide. So it will give you a conductive. It will become a conductive carbon or okay. So conductive mat kind of a fabric mat it will given, and pattern carbon fiber or fabric mat. Use ultra thin carbon sheet as has limited flexibility. Interface properties between the carbon structure and substrate are very important. So here you can see the flexible carbon structure made of laser carbonization. So here this is a laser induced carbon, and here this is your silver electrode, and this is your RGO patch, and this is again contact. So here you will have a contact resistance between your this two material, because this is your RGO, this is your silver. So this is flexible carbon structure by printing carbon nano material. And here you can see a flexible carbon fiber based carbon neural sensor. So this is a kind of a it can be used for the neurosurgery in order to get detect of your brain activity. So they have experimented in the mouse, and here you can see this is a brain signals, which is nothing but the called the EEG or brain signals that you can get from the inside of your brain. And yeah, so basically this is all for today's, and there are some more concepts such as your supply chain. So supply chain is very important, so this I will be supply chain of activated carbon. How it will usually done? So you will have AC manufacturer. So to AC manufacture your coconut shell, seeds of dates, leftover from the oil making. So that will go to your activated carbon manufacturer. So they will have a warehouse one and two, and this every warehouse will have a distributor one, two, three, and some many more. So every distributor, suppose water, this distributor one will give to the water filter manufacturer, and it will give to the cosmetic manufacturers. And suppose let's two will give to the cosmetic manufacturer and the air purifier. Three will give to the air purifier startup and the water filter. So they have some different distributors, and that will supply to that particular manufacturer. And this water filter manufacturer, other AC manufacturers will given to them, and then it will go to the in-house AC activated carbon manufacturing. So they will have a vast range of this supply chain. Similarly, for the carbon fiber, you will have this manufacturer, and then there will be two kind of a high modulus and the low modulus. So this high modulus will have a different fiber range, such as your short, braided, and research grade, and that will go to the customer. For your low modulus, you will have this braided and the short. So depending on the short fiber or the braided, it has a different application, such as for your biomedical implant or the CFRP performance or perform, or it can be used for your automobile part. So these are some supply chain that where the manufacturers, and there will be different distributors, and that will be go for the different kind of application. So this is all about this, and these are some good materials or books and some publications that where you can use these publications can be used in order to get a better knowledge and the essence of this subject. So so yeah, I hope that this session and this all the tutorials from week 1 to week 12 helped you a lot, and that is very essential, and you hope you guys have a good learning and good knowledge from this subject. And if you will have further any doubt or query, let me you can also give me a mail, or you can put in the comment box in my YouTube channel where I will upload my video. And hope you have learned a lot from this subjects, and hope to best of luck for your exams. Thank you.